Okay. So I'm going to make a recording of this discussion, and then so that you can refer to it. But how many are looking at MATLAB assignment number 2? How many see it and are looking at it on their own computers? Good, good. Thank you, Abby. And I know you're not working on the homework because I deactivated it. You know, I want you to pay attention here. Let's make sure everybody, I want everybody looking at this MATLAB assignment 2. Okay, thank you, Ariana. Thank you, Naima. All right, who else is looking at it? Let's just have maybe a few more thumbs ups. Excellent, excellent, Olivia, Benjamin, marvelous, wonderful, wonderful. Excellent, thank you, Eleanor, thank you, Peter. So we learned that computing a determinant by cofactor expansion is very difficult. It's very time consuming, and so in order to compute determinants quickly, we have to use the properties of determinants to help compute the determinants of matrices. And of course, you know, the 4x4 matrix, 3x3 matrix, it's not maybe so necessary, but if you have a 1,000 by 1,000 matrix, it is going to be necessary, you know, to use the properties of determinants. So the question is, how does MATLAB compute a determinant? Well, all right, it's going to use properties of determinants, but it does it in a little bit different way than you might think. So it says here, the MATLAB function, okay, LU parentheses A, uses Gaussian elimination to compute a lower triangular matrix, okay, an upper triangular matrix, and a permutation matrix where P times A equals L times U. So L times U is LU factorization. Remember, you can take a matrix and you can write it as a product of a lower unit triangular matrix and an upper triangular matrix. But in section 2.5, when you learned about LU factorization, you didn't have any row interchanges at all. Okay, you did LU factorization without row interchanges. But in fact, programs like MATLAB use row interchanges to do the LU factorization. Okay, and the reason that they do that is because programs like to use partial pivoting when they do their Gaussian elimination. Gaussian elimination is the same thing as row reduction. Okay, that's what Gaussian elimination is. So, and I'll show you why that why that's helpful to this partial pivoting. So partial pivoting is where in a column, okay, like normally when we do row reduction, okay, in a column, do we use the smallest number in the column as a pivot, or do we use the largest number in the column as a pivot? What do we tend to do? Use the largest number or the smallest? That's right, Eleanor. We use the smallest. And in fact, if that number is a 1, that's just great as a pivot. But we always, as humans, use the smallest number as a pivot, okay, for our row operations to produce zeros in the rest of the column. But in fact, programs like MATLAB will use the largest number in the column as a pivot. And the reason they do that is because it helps reduce round-off error. And I will show you an example either later today in a separate recording or on Wednesday of how that is helpful. But that being said here, let me just see here now. One moment. One moment, class. So the LU factorization, when you include, so normally you're used to seeing A equals L times U. Okay. Matrix factorization A can be written as a product of a lower unit triangular matrix times an upper triangular matrix, or an upper matrix in echelon form. Okay, but now if we're going to allow row interchanges, we have to represent the LU factorization by P times A equals L times U. Okay, and P is what's called a permutation matrix. A permutation matrix is a product of row switching matrices. So if we're going to include row interchanges to get our LU factorization, the equation is, the matrix equation is P times A equals L times U. Now, let me show you why that's true. Okay, let me show you why that's true. So on that note, let me go ahead and go to a little example, of this to demonstrate P times A equals L times U. Right. So let me go ahead, and then we'll go back to the MATLAB assignment. We'll continue on with what they're talking about in the thing, in the introduction. Okay, so what I have here in our discussion is I have a matrix A. Well, let me let you copy the example down first, okay? Let me give you a moment to copy the example down. Okay, and I know you're copying. I sent one of you all a little message. Okay, chat message. Okay, and I sent another little chat message to one of you. Okay, so let's see here. So in this little discussion example, and again, this discussion example is I'm doing this so that you can understand what the introduction into MATLAB Assignment 2 is talking about, so you can understand what they mean. So we want to find the permuted LU factorization of the matrix A, referenced in section 2.5. So in 2.5, they mention about the permuted LU factorization. They mention it in passing in section 2.5, just before the numerical notes in section 2.5. And permuted LU factoring uses partial pivoting, and that's referenced way back in section 1.2. So again, partial pivoting is where you use the largest number in a column to produce zeros in the other entries in the column. But again, we use the smallest number as a pivot as humans, but computers will use the largest number as a pivot. That's called partial pivoting, and there's a numerical note that comes at the end of example 3 in section 1.2. So we're going to justify this, and then we're going to use the resulting matrix equation, P times A equals L times U, where P is a permutation matrix, to compute the determinant of A. All right, so may I proceed on to the next page? Want to make sure I'm not going too fast. Okay, good, good. Thank you. Thank you. Okay. All right. So incidentally, before I go to the next page, in the first column, what's the largest number in the first column? A 4, right. So if we were to use the 4, thank you, Nafani, in the first column, if we were to use the 4 as a pivot, what would we have to do with the first and third rows? Hold on, let me go back here. So we're going to use the 4 as a pivot. But let me ask you, the pivot in the column, when we start our row reduction, is the pivot traditionally at the bottom of the column or at the top of the column? Where do we like our pivots to be when we're doing the forward phase of the row reduction? Good. That's right, Samantha. That's right, Hung. At the top. At the top. So what row operation am I going to need to do here to start to get this 4 where the 1 is? Good, I have to do a row interchange. I have to switch rows 1 and 3. Okay, so now in our mind, we know we're going to switch rows 1 and 3. How do we represent that mathematically? Here's how we represent it mathematically. Okay, we're going to take the elementary matrix E1 and multiply it by the matrix A. What is this element? What is an elementary matrix? Where does an elementary matrix come from? Okay, don't worry about the E2 right now. Focus on the E1, that elementary matrix. It kind of looks like an identity matrix, doesn't it? Except what? I mean, we know it is an identity matrix, but gee, you know, if we were to take the identity matrix and do a row operation on it to the identity matrix, it could look like the elementary matrix E1 here, right? It could look like that. Well, what row operation would we have to do on the identity matrix to get the elementary matrix E1? An interchange. Excellent, Haley. And what rows would we interchange? Rows 1 and 3. Rows 1 and 3. Very good. Very good, Hung. And I appreciate all participation. And if you look here at this elementary matrix, okay, clearly I took the identity matrix and I switched the first and third rows. Okay, so the effect then is if I take E1 and multiply it by that elementary matrix and multiply it by A, I'm going to get this matrix here. And this matrix here is the matrix A with the first and third rows interchanged. Okay. So let you copy down to here. I want to make sure, you know, that folks are comfortable. All right, so let me give you a moment to catch up to here. Please let me know if you have any questions. Okay, all right, so let's continue now. Let's continue. So for the first column of this 3 by 3 matrix, the first column of this 3 by 3 matrix, and maybe I'll you know, clear here a little bit. This 3 by 3 matrix here is equal to E1 times A, elementary matrix E1 times A. And I'm going to use the 4 here as a pivot to produce zeros in those two spots below 4. Okay, so then I know that that can be done. All right, that will be done. But let's talk about the second column. Let's talk about the second column. So what normally would we use as a pivot in the second column to produce a 0 where the 4 is? What number would be used? Think about your row operations. So I'm focusing on the second column. I'm thinking ahead a little bit here. I know the second column, I want to get, I want to reduce the matrix A into echelon form. So I want to have a 0 right in this spot here. So if I wanted a 0 right in this spot here, what would the pivot be that I use? What number? In the second column. That's right, Lewis. We would use the 3. We would use the 3, but would MATLAB use the 3? Or would MATLAB want to use the 4? What number is MATLAB going to want to use as a pivot? The 3 or the 4? It's not going to use the 8, right? Because this is the forward phase of the row reduction. But with partial pivoting, what pivot would MATLAB? All right, MATLAB, good hung. MATLAB would choose the 4. Well, okay. If MATLAB chooses the 4, then we need to move the 4 up 1. Okay, we need to move the 4 up 1. So what rows have to be interchanged then for this matrix? If we want the 4 to be in the second row, good hung, we have to interchange rows 2 and 3. Okay, well, the elementary matrix to interchange rows 2 and 3 is right here. That's the elementary matrix E2. The elementary matrix E2 comes from the identity matrix where we switched what rows? Oh, wait, hold on. No, let me fix that. Hold on. That's not right. Let me fix that. I mean, hold on. Let me go back here. So again, here's the matrix, right? This equals E1 times A. And we're happy with the first column because the 4 is going to be used as a pivot to produce zeros below it. Now we want to get a 0 in this spot here. If we continue the row operations, we would want to get a 0 in this spot. But 4 and 3, okay, we would normally, as humans, we would use the 3 as a pivot, but with partial pivoting, we pick the larger number as the pivot, which would be the 4. So in order to get the 4 in the second spot here, we have to do a row interchange of rows 2 and 3. And that's what elementary matrix E2 is. Elementary matrix E2, look at rows 2 and 3. Elementary matrix is the identity matrix with what rows interchanged? Good, that's right, hung. E2 is the elementary matrix where you interchange rows 2 and 3. So if you want to interchange rows 2 and 3, on this matrix here, you're going to multiply it by this by this E sub 2 matrix. Okay, so we're representing the row operations mathematically by multiplying by elementary matrices. Now, if you take E2 times E1, you're going to get this matrix right here. You're going to get this matrix. The product of elementary matrices E1 and E2 is called your permutation matrix. Okay, that's called your permutation matrix. What does permute mean? To permute something. How many have heard of the word permute? That's right, Benjamin, arrange. Arrange the order. And that's what this permutation matrix does. It arranges the rows of the matrix A. Okay, so if you take the permutation matrix and then multiply by E1 times A, then you're going to get this matrix right here. And now this matrix is in perfect form for MATLAB because the pivot 4 here is at the top of the first column, and the pivot, and it's the largest number, and then the next pivot 4 is in the second spot, and it's the largest number. You know, we don't worry about the 8, right, for getting the matrix in echelon form. So your pivots are where you want them to be, and naturally, you're not gonna worry about the last column, right? So, all right. So you need to allow interchanges of rows for this to happen. Okay, and this is what differs from your section 2.5 LU factorization. In section 2.5, when you did the homework, you didn't do any row interchanges. Hold on, there was a chat message here, one moment. Hold on, class. Haley asked a question. That's correct. This matrix here, and that's why I have the big, I have the big bracket here. Yeah, this matrix here is the product of E2 times E1 times A. That's right. That's exactly what this is. Make that a little bit nicer here. E2 times E1 times A. That's what this is. That's what this matrix is. And incidentally, E2 times E1 times A is equal to P times A, because the product of these elementary matrices that do the row interchanges is called your permutation matrix. Haley, does that answer your question well? Excellent, excellent. All right, now let me ask you then, what is this going to equal then on the right side? What's going to go on the right side here? Well, it's a matrix factorization. A is going to equal we want to do a matrix factorization. A is going to equal the product of two matrices. What do we want those two matrices to be? I need two letters. Think of section 2.5. Good. Good, Benjamin. Good, Hung. L times U. Right? And what you're used to seeing is A equals L times U. But because we're now including row interchanges, the matrix equation becomes P times A equals L times U. So we're going to be doing LU factorization on this matrix here. This matrix here. I'm circling it a lot, so you'll see it in the recording. We're going to be doing our LU factorization on that matrix. Okay, may I move to the next page? Because now I'm going to show you the LU factorization. Are there any questions? All right, Nafani's good. Abby's good. Okay, so I'm gonna just show you the matrix factorization. We can easily work it out by hand, but MATLAB is going to do LU factorization on this matrix here. On this matrix here. So if I go to the next page, okay, here's that matrix. And what I do is I take negative 1/4. So the first column, I'm using the 4 as a pivot. So I'm taking negative 1/4 times row 1 plus row 2. And replacing row 2 with that result. And then I'm going to take negative 1/2 times row 1, add it to row 3, and put the result in row 3. Okay. And I have a little note here that 2 row interchanges were used. Should be a word. We're not doing them now. Now we're done with the row interchanges. But we just remember that 2 row interchanges were used to get to that matrix. But now what we're doing is strictly row operations where hold on. Now we're doing row operations where I want to say it the right way. Hold on. Yeah, now we're just doing row operations where we replace, where we, I'm sorry, I want to use the exact words here. One moment, class. One moment, one moment. Should be easy to find. I'm looking in the book, trying to find the right terminology here for the row operations. Oh my goodness, hold on. This should be like, okay, yeah, elementary row operations, section 1.1. So now I'm doing replacing a row by sum of itself and a multiple of another row. That's what I'm doing. Okay, and then to get to this step here, finally, let's see, I'm going to take, so now I want to use the 2 to produce a 0 where the -1 is in the second column. So we'll take 1/2 row 2 and add it to row 3. Okay, and replace row 3 by that result. Okay, and now the matrix here is in echelon form. It's upper triangular. And of course, as you learn from LU factorization, you remember that when you do the LU factorization, of course, when you start off, you have your first column here, and you bring the first column down here and divide the first column by 4. That's the algorithm. And then you'll take a portion of the second column, bring that down here, and so that you can get a 1 where the 2 is, you divide by 2. Okay, and then finally, where this step here, the -1.5, you bring that down here and you divide by -1.5, so you can produce a 1 in that spot. And so then you'll get your lower unit triangular matrix. How many does this ring a bell, this process? It's been a little while since you've seen it, but how many? Okay. You'll be doing it on the exam, right? All right, very good, very good. Excellent. Okay, so now, see if what this matrix U here, this matrix U, this matrix L, and the matrix P on the previous page, that permutation matrix, are going to show up when you do your LU factorization. Okay, so what I want you to do is I want you to go into MATLAB, and I'd like you to type this matrix A. Okay, and I'm doing it as well. So you're going to go into MATLAB and type the matrix A in the command line. One moment, class. Hold on, class. One moment. I'm going to go into, I'm in MATLAB now. I'm just, okay, good. Okay, let me bring up MATLAB. So it's on the recording. Are there any questions here? Okay, then let me go into MATLAB. And this is all in the recording, so you can review this when you're working on MATLAB assignment 2. So it helps you understand what you're doing. Can everybody see my MATLAB screen all right? Excellent, excellent. Okay, so the matrix A, I typed it in, and there it is. You know how to type a matrix in MATLAB. And the LU factorization, the command is LU of A. But what I'm going to do is I'm going to create an array of matrices that when MATLAB does its LU factorization, it can store the lower unit triangular matrix, L, the upper triangular matrix U, and the permutation matrix P. It'll store them and show them. That's why I have on the left the LUP there in the braces or the brackets, I guess. So if you type that in and hit enter, okay, you get the matrix L, the matrix U, and the matrix P. Now, does the matrix L match what you copied in your notes? Hold on here. Does the matrix L match what you found? It does. That's right, Ariana. Absolutely. That's right, Nafani. Does the matrix U, thank you, Abby. Excellent. That's right. Does the matrix U match what you did in your notes? What you have in your notes? It does. It does. Very good, Abby. Very good, Nafani. And what about the matrix P? Does that matrix P match the permutation matrix that you have in your notes? It does. It does. Thank you, Ariana. Are there a few more confirmations on this? So I'm wanting you to go back to the notes you copied and check that everything matches. Good, Nafani. And maybe one more person. Give a thumbs up. Okay, excellent, Abby. Excellent. Thank you, everybody. Thank you, everyone. So now you know what MATLAB's doing. You know what MATLAB's doing, how it's doing this permuted LU factorization. Okay, and now the question is, well, how does this help us with computing a determinant? How does this help us? Okay, well, let's go back to the notes that we were looking at here. All right. Okay, so we found L and U. Okay, we have, hold on here, we have that matrix L. We have the matrix U. And we have this matrix P here, right? That's that matrix P, the permutation matrix. And we have the matrix A. And we know that P times A equals L times U. And based on that matrix equation, we can see how easy it is for MATLAB to compute a determinant. Because we can mathematically see it. Because, okay, what can we do with this matrix equation? Well, we can take the determinant of both sides of that matrix equation. The determinant of P times A then will equal the determinant of L times U. But you learned that the determinant of a product of two matrices is equal to the product of the determinants. Okay, so the determinant of P times A equals the determinant of L times U. But the determinant now on the right-hand side, the determinant of L would just equal 1. Because L is what kind of matrix? What form is matrix L in? You know, why is the determinant of L just equal to 1? That, well, all right, Hung, matrix L is in, you're right, we're using the diagonal. Matrix L is it's in echelon form, and there's a word I'm looking, okay, it's also in triangular form. And so, but you have the right idea. Because the matrix L is in triangular form, okay, that means that the determinant of the matrix L is just the product of the diagonal entries. How many remember seeing that in their homework for section 3.2? Problem or two with that idea. Sure. Hung remembers it. How many of you remember that? When you have a, sure, and that's the whole idea, right? To get the matrix in triangular form. Thank you, Eleni. So now on the left side, the determinant of P, that permutation matrix, is going to equal -1 squared. Because 2 row interchanges were needed, the determinant of P is just equal to -1 squared. Okay. How many recall that rule? That rule. That's one of the matrix rules, right? When you take a matrix and you do a row interchange, it introduces a -1 in the determinant. And if you need R number of row interchanges, if you do R number of row interchanges on a matrix, the determinant, well, want to be a little well, the determinant of the matrix P is going to equal -1 squared because 2 row interchanges were needed. So if you take an elementary matrix and you interchange rows R times, the determinant is just going to be -1 to the rth power. Okay, how many feel comfortable with that based on their knowledge of properties of determinants for matrices? How many are comfortable with that? Okay, good, Benjamin. Good, Nafani. Excellent. I'm seeing. Thank you, Ariana Travani. A lot of comfort here. Good. So, but of course, we want to figure out what the determinant of A is. Well, look at what we got here. All we need to do is take the determinant of A, and that's going to divide by that -1 squared. So the determinant of A equals the determinant of U divided by -1 squared. And so the determinant of A is just equal to -1 squared times the determinant of U. And the determinant of U is easy to get. That just equals the product of the pivots in U. U is an echelon form. And so this now relates to the formula in section 3.2. That formula on page 173 that we talked about last time. So So you see that now you have a very simple formula for computing the determinant of a matrix A. Very simple formula. Okay. All right. And I'd like to now go back to MATLAB assignment 2, just to sort of conclude things regarding the introduction. But are there any questions on are there any questions? How many are comfortable? Reasonably comfortable, I should say, with what you're learning here. Excellent, excellent. Thank you, Eleanor. Thank you, Olivia. May I go back now to the MATLAB assignment 2? Are we good here? Thank you, Naima. Okay, Nafani, thank you. All right, then let me go back to MATLAB assignment 2 here. One moment. Okay. All right. So now you can understand. So everybody can see the MATLAB assignment 2 all right? In the okay, wonderful. Thank you, Shivani. So now you know where this comes from. Determinant of P times determinant of A equals determinant of L times determinant of U. And so it follows that the determinant of A really can be represented as just plus or minus times the determinant of U. Absolutely beautiful, an absolutely beautiful result. And so you have several exercises in MATLAB assignment 2. Okay, several exercises. And now I think it should make they should make better sense. Are there any questions? How many think this is really a pretty cool thing that you've learned, this way of computing the determinant of a matrix A? I mean, the fact that the determinant of A is equal to plus or minus depending on the number of row interchanges, right? Because that's the -1 to the rth power part. Determinant of A is plus or minus determinant of U, where U is an echelon form. Olivia thinks definitely. Are there maybe a few more people that think that this is cool? All right, Nafani thinks it's cool. All right. Maybe, so we have 2 people that think it's cool. Okay. All right. Thank you, Andres. All right. Good. All right, Abby. I love it. It's amazing. I love it. All right. Great. I think it's great. Now, let me see here. A question. So for Andres, you have to basically then, so like for MATLAB exercise 1, you're going to compute the MATLAB to compute a determinant. There's a command called DET of A. So MATLAB exercise 1, DET of A computes the determinant. But what you're going to do is you're going to check that result using finding the LU factorization of A, and then utilizing the formula here. So as a check on the determinant of A, you're going to check it by computing plus or minus the determinant of U. But of course, plus or minus is going to, how do you find plus or minus? Where would that come from? That would come from, so think about the little formula here, and and I think that's a, I don't want to, I mean, I think you can kind of figure this out, but you're going to check the determinant of A in MATLAB by this formula here that I've highlighted in blue. Does that help, Andres? Does that help? And Andres likes it too, what he's learned. Wonderful, wonderful. Okay, all right, let me stop the recording here.